and welcome to our Consulting Specifying Engineer video discussion. I'm your host, Amara Rausgis, and today I'm speaking with Hassan Obaid from Cummins. Hey Hassan, how are you?
Hey Amara, how are you?
Good, good. Well, thanks for joining me. Um, Before we get to the technical aspects that I want to talk about today, let me provide some background. Hassan Obaid is a global technology sales leader, new energy solutions at Cummins Incorporated. His focus is on distributed generation, microgrid applications, and integrated system solutions encompassing energy storage, fuel cell power systems, controls, and energy modeling. Hassan has been with Cummins since 2007 in a variety of roles: technical advising, design engineering, project engineering, and application engineering. Hassan has designed power systems involving energy, storage, fuel cells, generators, controls, transfer switches, switchgear, and microgrids. Wow, okay, that's a lot. Um, Let me start with an absolutely basic question, Hassan. What are the key considerations when designing battery energy storage systems, known as BESS, for either a commercial or an industrial or a mission critical application?
Yeah, so when designing BESS or BESS for commercial, industrial, and mission critical applications, it starts with clearly understanding the use cases, whether it's peak shaving, backup power, renewable integration, or energy arbitrage. Each use case has unique power and energy requirements, which define the appropriate discharge duration, C rate, control strategies, and of course, codes and regulations, so codes and standards. It is also critical to define the beginning and end of life energy requirements, and usually that's defined in watt hours or megawatt hours or kilowatt hours. Environmental and space constraints are also major factors, especially in retrofits or urban deployments. When we need to consider also interconnection requirements with the utility, even when operating behind the meter. So depending on the use case, of course, or within a microgrid and ensure compliance with local codes and permitting. And finally, control system integration is essential. How the BESS will interface with microcontrollers, SCADA systems, and existing infrastructure often dictates the success of the deployment.
Okay, so then how do you see battery energy storage contributing to carbon and emission reduction efforts, or like when you're integrating it with renewable energy sources?
Sure. So BESS plays a central role in enabling the energy transition. When combined with renewable energy sources like solar or wind, it allows for storing energy during periods of excess generation and dispatching it when the demand is high. Essentially, time shifting clean energy to when it's needed the most. This helps reduce reliance on fossil based peaker plants and minimizes curtailment of renewables. In microgrids, BESS stabilizes the system, smooths intermittent renewable output, and supports loads during outages, allowing diesel off or reduced diesel operation. This is particularly important in remote industries or campus style grids. Amara, for a broader sustainability perspective, BESS helps organization reduce what's called Scope 2 emissions and optimize demand side energy, contributing to both environmental goals and long-term cost savings. You might hear the term Scope 1, Scope 2, and Scope 3. Scope 2 emissions are indirect greenhouse gases, GHG emissions that result from companies' purchase of energy such as electricity, heat, steam, or cooling from an external source.
Okay, and you mentioned this, Hassan, but what are the primary codes and standards that engineers need to be aware of when they're designing or deploying BESS solutions? And how are they changing?
Yes. Yeah, and some are actually changing. So there are several critical codes and standards that consultant engineers must be familiar with. In the United States, NFPA 55 outlines installation requirements for stationary energy storage, while UL 9540 and 9540A address system level safety and thermal runaway testing. Of course, we have IEEE 1547 that governs interconnection standards, especially for grid-tied systems, and the National Electric Code, or NEC, specifically Articles 706 and 480, provides electrical safety and wiring requirements. There are also international standards, so standards like IEC 62933 and 62619 are also important, especially, like I said, for multi-region deployments. What's important to note is that these standards are rapidly evolving as energy storage adoption accelerates. For example, NFPA 55, that's next year's edition, so 2026, will introduce significant changes to energy storage system installation standards, including a separate large-scale fire test, LSFT, requirements, stricter fire and explosion testing protocols, and enhanced requirements for deflagration prevention.
Got it. So, what are the most common applications of BESS today, and how do they differ, both in design and implementation across various industries? We talked about mission critical, we talked about a couple different things.
Absolutely. The most common BESS application include peak shaving, backup power, renewable energy integration, and grid services. It's important to note that solar and wind are intermittent resources. And so we can use battery to couple with those intermittent resources. So we store the energy when the wind is blowing and when the sun is shining at times when you really don't have enough loads to consume all that power. So we don't have to do renewable curtailment. So this is where BESS fits in. In commercial and industrial settings, BESS often used for demand charge reduction and time of use shifting, or TOU, which typically calls for short duration, high power systems. In mission critical environments like data centers, BESS can be applied in demand response or grid augmentation, particularly when utilities are unable to meet this high demand from these facilities. We see another use case for BESS in data centers in addressing this is called a short duration, high power load oscillation that is generated by GPUs during AI training. For utilities or large-scale campuses, BESS is used to support renewable integration and provide what's called frequency and voltage support. And this is when IEEE 1547 comes in handy for that requirement, which demands longer duration systems and advanced control capabilities and inverters. So for utility scale, you might see batteries that go 4 to 6, 8, and 12-hour duration batteries.
Okay. So let's shift gears just a little bit here. What are some of the main technical challenges when synchronizing or load sharing BESS with traditional synchronous generator sets in a hybrid power system?
So one of the biggest technical challenges in hybrid systems is managing how BESS or BESS and traditional synchronous generators share load and synchronize. BESS can respond almost instantly to load changes, while generators are inherently slower a bit. Without proper coordination, this mismatch can cause load oscillations or reverse power flow. Synchronization is another critical aspect. When BESS is used in grid forming role or a transitioning between islanded and grid connected modes, the system must ensure proper voltage, frequency, and phase alignment. The three important things: phase, voltage, and frequency. It also becomes essential to define clear control hierarchies, especially through a microcontroller, to ensure all sources are coordinated correctly during normal operation, transition, and faults. Additionally, it is important to note that because BESS contributes limited fault current, protection schemes must be carefully engineered to maintain safety and continuity during fault conditions. The basic control algorithms such as synchronizing, which is for the phase, voltage, and frequency, are typically inherent in the inverter itself, just like a synchronous generator has the capability to match phase, voltage, and frequency. Load sharing is a little bit trickier. There is no common architecture to load share like isochronous load sharing that we see typically today across synchronous generators, for example. So we don't see a common protocol between a battery and a synchronous machine. Therefore, other methods are used to handle load sharing for this aspect.
Okay. Okay. So looking at sizing, can you talk about how to size these battery energy storage systems, like the number of batteries or energy calculations?
Yes, absolutely. We need to also establish that something very critical when it comes to batteries. A synchronous machine, for example, today that you deploy that's 1 megawatt or 2 megawatt in 5 years, in 10 years, in 30 years, it's still 1 megawatt or 2 megawatts, right? So that power is still the same and the same amount of energy. Battery degrades over time. So today, a battery that is a 2 megawatt hours in 6 months, we're going to lose a few percentages, so on and so forth. So in 10 years, there's a potential that capacity will go down by 30%. So it's at 70%. And this is typically for stationary application, what's considered end of life. So it's very critical when you're specifying a battery. Obviously, yes, we need to know the requirements, codes, voltage, frequency, temperature, and load profile. But it's also important to also state what is the requirement for the end of life, or after 3 4 years, after 5 years, what is required for the energy? Are we expecting the same amount of energy at the end of life? If that's the case, that means we got two options in here. We either have to oversize the battery at year one. So if the project only calls for 2 megawatt hours, but in year 10, we also want to see 2 megawatt hours, we might have to go with 3 containers or 2 containers. So we might have to go up to 4 or 6 megawatt hours in year one to give me 2 megawatt hours at the end of life. Or the other option would be augmentation. So every 3 to 4 years, we add more batteries, augment as time goes by to maintain what we need at year 10 or the end of life.
I know my next question is top of mind for a lot of fire protection and life safety engineers. Tell me about safety considerations. What are those considerations? What are some mitigation strategies when you're designing or deploying a BESS system?
Yeah. So safety starts at the cell level and extends all the way to system integration and operations. Key considerations include thermal management, fire detection, suppression system, and emergency access. BESS should have active thermal control and must be monitored continuously to detect any anomalies in temperature or voltage. Based on the outcomes of UL 9540A, which is the testing for thermal runaway, enclosures may require specific containment or spacing strategies to prevent thermal propagations. Fire suppressions could involve inert gas, water mist, or aerosol systems, depending on the installation type and local codes. You might have smoke detectors, lithium-ion particle detectors. For example, the Cummins battery has multi-levels of safety built inherently into the battery itself. From a design perspective, ensuring proper spacing, aisle access, separation from occupied areas is critical, especially in NFPA 855 compliant deployments, which I mentioned earlier. Beyond the hardware, having well-defined commissioning protocol, operator training, and emergency response plans are all part of this holistic safety strategy. Ultimately, safety isn't just about compliance, it's about proactively minimizing risk throughout the system's life cycle.
Great overview. Thank you so much, Hassan.
Thank you, Emma. I appreciate it.
Yeah. And once again, that was Hassan Obaid from Cummins, focusing on battery energy storage systems. I'm Amara Razgas with Consulting Specifying Engineer. Make sure to check out our YouTube channel and website at www.cscmag.com for more coverage of this topic and for similar electrical and power content. Thank you so much for joining us. Bye-bye.